it going, chemistry? It's Mr. Nunez here, and today I just want to recap what we learned last week because we've got a unit exam on Friday, a reassessment tomorrow, and I think some of us are just way in over our heads about what the heck was going on. Plus, with the amount of tech issues, I mean, I could go on and on for why we need this. But today, I'm going to give you a week one recap. You will learn the parts of an atom, atomic mass versus, atomic number versus mass number. What is an isotope? Calculating the mass number. How the heck do you read the periodic table? You should definitely have this video on your screen because you're watching it right now, and you should have something to take notes with. If you want to take notes in your OneNote to keep everything organized, at the bottom there is a button that says Add Page. If you hit that button, you will get a new page which you can rename. I recommend renaming it to Week 1 Recap. And then you can click anywhere to start taking notes. You can draw, all of those things. So if you need to do that right now, go ahead and pause this video so that you can get your notes open. Now that you've got your notes open, let's just look at a brief history of what an atom looks like. Remember, if you don't see that little symbol in the bottom right hand of the screen, you do not need to be taking notes on this. In 1803, we got our first idea of what an atom looked like. Some scientists figured, well, if we were to break things down really, really, really small like sand, and then keep breaking it down really, really, really small, it'd probably be made out of a bunch of spheres that are all locked together somehow. That's going to make everything else in the universe. And then somebody came along and said, wait a minute, some things seem to attract other things in this weird sort of charge. So maybe actually it's a collection of positive and negative charges that are all just kind of mishmashed together. Well, then somebody else came along and said, no, they're not mismatched together. You've got the positive stuff on the inside, you've got this negative stuff on the outside. And somebody else came along in 1913 and said, hey, you're onto a pretty good idea right there, except it's not just all hanging out in one space around the outside. It's actually in a bunch of different spaces, and it orbits the center, kind of like the planets do. And then about 13 years went by, and somebody else came along and then said, wait a minute, we have some advanced technology now. We know that the center is all the positive and zero stuff. And all this negative stuff just can randomly move around wherever it wants on the outside. But we can predict where it's going to be. Now, you don't have to necessarily know the details of that until this week, but you should know that that's what the atom looks like today. And then finally in 2018, almost 100 years later to the day, we got our first picture of an atom. It's that tiny speck in the middle, and it kind of looks like what the guy in 1803 said, so who really knows who's right? We do. It's this guy. All right, now you're going to want to start taking notes. I want to break down the parts of an atom, and there are three things that you really need to know. In the center, we have what's called the nucleus of the atom. Okay? The nucleus has two things inside of it. It's got a proton and it's got a neutron. The proton has a positive charge. We've known that since as far back as 1904. There's this positive charge hanging out in the atom. We go ahead and just say, too, that the proton has a mass. And when they weighed it the first time, they said, well, we don't know what anything else weighs, so we're going to say it weighs 1. 1 what? 1 atomic mass unit. The scientists weren't working too hard when they came up with a name for this. They said, well, the proton gives it mass, so it's the atomic mass unit. We will go ahead and write this as 1 AMU. Glued to the protons are all positive. Glued inside and between them is what we have, what we call the neutron. A neutron has a zero charge. Okay? And when they weighed the neutron, they didn't just put it on a scale. They have very fancy ways to do that. Wish we could do those in class. But to weigh a neutron, they found that it had basically the same mass as a proton, and so they said, hey, this thing also has a mass of 1 AMU. And so the stage was set. We have protons and neutrons in the center. They're very heavy. They've got 1 AMU each. We're going to go ahead and write protons with the shorthand P with a superscript plus. That means it's hanging up kind of like an exponent. And a neutron as an N with a 0, kind of like a superscript. And that just lets us know that the proton is the positive, it's got the plus, and the neutron is neutral, it's got 0 charge. Neutral meaning no charge. And then later on they realized it's not just this heavy stuff in the middle, there's also these things that are seemingly flying around. And those things are called the electrons. An electron gives an atom its negative charge. And then when they tried to weigh it, it turned out it was really hard. They just assumed it was going to be 1 AMU as well, but it wasn't. It turns out it's about 1/2000th of an AMU. You're like, whoa, that's a big fraction. Here's the nice thing. We're going to say that this is basically 0. You know how in class, whenever you have a decimal, you just go, we'll just round it. That's basically what scientists do all the time. But it's not actually 0. It's 1/2000th of an AMU. It's very, very, very small. We're going to go ahead and write electrons as a lowercase e with a superscript minus sign, which lets us know we're talking about electrons, and they are negative. So those are the 3 parts of the atom. Please do not forget these. They're the foundation for everything else. Literally, atoms make up everything. Whoa. So now we can talk about the atomic number and the atomic mass. Scientists are never happy with one name for things. They like to give things 2, 3, 4, 5, 6 different names. Atomic number is one of those examples. An atomic number is equal to the number of protons in an atom. Okay? So my diagram over here, the red represents the protons. There are 3 protons, so it has an atomic number of 3. Okay? If you are talking about a neutral atom where all of its electrons and all of its protons cancel out, which is everything we're going to be talking about last week and this week, then that means this is also equal to the number of electrons. We will break this rule starting at the end of this week. We will start to break that rule. But if you're watching this on Tuesday like you're supposed to, just know the atomic number is also equal to the number of electrons, unless we tell you otherwise. So then where does this atomic mass business come from? Okay? The atomic mass is equal to the number of protons plus the number of neutrons. Okay? So in our picture right here, we have 1, 2, 3 protons. So that would be 3 AMUs plus the number of neutrons, which is 1, 2, 3, 4. So that would be 4 AMUs. And so the atomic mass number of this guy is 7 AMUs. The biggest mistake I saw was that the atomic mass is equal to the number of neutrons. If you do that, I will cry alone in my bed at night. It is not equal to the number of neutrons. It is equal to the total of protons and neutrons added together. Okay? Let's see if I can erase this. So add those 2 things up, you get your atomic mass. They are not the same thing. Okay? One is just the number of protons. The other one is take that number, add it to your neutrons, and you get your atomic mass. Easy enough, right? So if we look at hydrogen in the periodic table, which we'll look at more closely at the end, hydrogen has 1 proton and 0 neutrons. Okay? So we have, for our atomic mass, we know that it is protons plus neutrons. And we know that there's 1 proton, so if we add our 0 neutrons, we should have an atomic mass of 1 AMU, right? Holy cow. Of course it has to be harder than that. If you look in your periodic table, the atomic mass of hydrogen is not 1. It's actually 1.008, which is basically 1, but it's not exactly 1. And that's where the real chemistry comes in. You might be thinking to yourself, oh, well, it's got to be the mass of the electron. And again, it's not quite that simple. An electron is too small to account for this much mass. So we need to look at something else. So this is where isotopes come in. An isotope is a chemical or a set of chemicals that have the same number of protons, but different numbers of neutrons. The most common example that are used in textbooks, but we didn't really talk about in class, are the isotopes of hydrogen. So we already saw the example of hydrogen with a mass number 1 that has just 1 proton and no neutrons. Well, if we throw an extra neutron in there, let me go ahead and just do this math really quick. If we throw an extra neutron in there, so now it's got 1, we've got 1 plus 1, so now we've got an atomic mass of 2. Okay, so then we've got hydrogen 3, well that would still be just 1 proton, remember same number of protons. But now we've got 2 neutrons, and so we've got an atomic mass of 3. Well, what the heck? Which one is it? As it turns out, there's also hydrogen 4, hydrogen 5, hydrogen 6, hydrogen 7. I mean, there are so many possibilities. So why do we care about all these different hydrogens? Well, hydrogen 1, this is a picture of hydrogen 1 in a bottle. It's just gas. You can't even see it. Okay, this is the stuff that's all around you. Wave your hand through the air and you're swatting around hydrogen 1 right now. Hydrogen 2 is actually used in nuclear reactors. And when it's highly charged, you can get this cool pinkish glow inside of it. This is also referred to as hard hydrogen, or sorry, not hard, heavy hydrogen. It's called heavy hydrogen because it's just like the regular hydrogen, but it's a little bit heavier. Hydrogen 3 is how your watches can glow in the dark. In fact, a lot of glow sticks and stuff might have hydrogen 3 in them. It's all this glowing material in here. It doesn't require any sort of nuclear reactor to make it glow. It does it all on its own, which is why we use it in those watches. 4, 5, 6, and 7, we can't get enough of it to stick around to use, so we don't really talk about what we use those for. And they don't have fancy names either. Before we can really understand where that 1.008 comes from, we have to understand what abundance is. Okay, so what is abundance? According to the dictionary, abundance is a very large quantity of something. Okay, it's also a bid by which a player undertakes to make 9 or more tricks. I don't know what that means. We're going to ignore that definition. An abundance is just the quantity or the amount of something. It's how much you have. Okay. It doesn't have to be a large amount in science. When we say what's the abundance, we just mean how much is there. And so when we're talking about hydrogen, it turns out that if you were to take a jar and fill it with hydrogen, 99.9885% of that would be hydrogen 1, no neutrons. But 0.0115% of it, so less than 1%, okay? That's hydrogen 2. So if you could zoom in really close, you'd see that proton, but you'd also see a neutron glued in there as well. Hydrogen 3, there's so little of it, that it's basically 0, but it's not actually 0. We do this in science all the time. We say it's basically 0.000000001, but that's close enough to 0 that we just say it's 0. But it's not actually 0, okay? So this gives us a clue then as to where the heck this 1.008 comes from. This is where we calculate the mass number. A mass number takes into account that not every atom comes in only one variety. In fact, no atom only comes in one variety. It comes in multiple isotopes. And so to do this, we need to take the mass of hydrogen 1, which is a mass of 1, and we need to multiply it by its percentage. We can't multiply by a percent, we need to multiply it by a decimal. And if you remember in class, I told you move the decimal over 2 times. So that would be 0.999885. Okay, and then we're going to add the other hydrogen. That's 2 times, and then we need to move our decimal over 2 times again. So that's 0.000000115. And then there's some other stuff in here that we can't really add. And if I plug this into my calculator exactly like this, we get a grand total of, and I promise I'm doing this right now, it's sitting right in front of me, here's my calculator, almost 1.007 with some stuff after it, and if we round it, we get 1.008 AMUs. So this mass number isn't just talking about the most abundant, it's talking about, in general, if we were to take into account all the different masses, what the average mass would be. Okay, so mass number, as it shows up in the periodic table, is an average mass of all isotopes. Okay, can't forget that. If I'm asking you to do a calculation, you should do it this way. If I just show you a picture of some protons and neutrons and say what's the mass, you just add them up. Okay? So I broke it down into 4 easy steps. You have these in your notes, but you should write them down again. Step 1, you need to find the missing percent. So if I told you, I never gave you this, and I said hydrogen 1 is this percent, you would need to find the percent of hydrogen 2. It always has to add up to 100. So it's not like the percent of 2 is also 99%, because 99% plus 99% is almost 200%. That's too much. Instead, take 100%, subtract how much you know, and you're going to get whatever is left over. After you found your missing percents, convert them into decimals. You can do that by moving the decimal over 2 times, or you can do that by dividing by 100, whichever you prefer. Next, you're going to multiply the mass of each isotope by its abundance. That's where I took the 1, which was the mass, and multiplied it by the abundance. Took the 2, which was the mass, multiplied it by the abundance. Make sure you're multiplying it as a decimal form. On our quiz, several people missed this because they forgot to change the percents into decimals, and it broke my heart. Finally, you need to add up whatever is resulting. I did that all in one step here, but you could do all of this separately and then add it all up at the very end, whichever you're more comfortable with. Finally, you need to understand how to read the periodic table. And I'm pushing 400 years old here, so I'm going to go ahead and zoom in on just this section right here. Great, there it is. And so you can see we're looking 5 through 10. There are really 4 things that you need to know. The atomic number. This is the number of protons. The atomic mass. This is the weighted average, of all isotopes. And then there's the name and the symbol. Okay? One thing I did not mention, let's back up just a little bit and let's talk one more time about what we call isotope notation. I forgot to make a slide for this, that's my bad. Isotope notation you can make by writing the element symbol. And then on the bottom, you're going to put the atomic number. So for hydrogen 1, that would be 1. On the top, you're going to put the atomic mass. That's just by adding up the protons and the neutrons. So for this isotope, because there's no neutrons, this would also be 1. But in our next example, the atomic number is still 1 because there's still 1 proton, but because it has a mass number of 2, that top number is going to be a 2. And then finally, the third one still has an atomic number of 1, but its mass is now 3 because there are 2 neutrons. You can do this with pretty much anything. If I told you that there was an isotope of, let's say, carbon called carbon-14, okay, let's go to the next slide for this, carbon-14, okay, that is an isotope of carbon. So what I'm going to do is I'm going to go to my periodic table, I'm going to find the atomic number, I see the atomic number is 6, I'm going to write C with a 6 on the bottom and the mass of 14. What if I told you that there was something called nitrogen-17? Well, this is an isotope of nitrogen. So I'm going to come to my periodic table. I see nitrogen. I'm going to find the atomic mass. So I'm going to write N for nitrogen. I'm going to put the atomic number on the bottom. And I'm going to put the atomic mass up top. How many neutrons does this thing have? Think about it. If you just said 17 in your head, you broke my heart again. To find the number of neutrons, take the mass. Remember, mass is protons and neutrons. Subtract the protons, and you're left with just the amount of neutrons. This is a big, fast recap of what we did last week. If you did not catch all of this in this watch-through, you should watch it through again, maybe 2, 3, 5, 20 times. I don't know, however much you need to feel confident with this material. If you have questions, put them in the comments section below on Teams. And if that's not enough, then go ahead and message me separately. Thank you guys, and I will see you